Hey everyone, and welcome to this explainer. Today, we're going to unpack one of the most genuinely fascinating concepts in modern data architecture. We are going to figure out how to untangle the messy, chaotic web of highly interconnected data. Look, if you've ever tried to build an application and felt like your own data model was, well, kind of fighting against you every time you just wanted to map out how different things relate to one another, you are in exactly the right place. The truth is, modern applications are fundamentally different from legacy ones. They're intensely connected. We literally expect our software to understand these vast, complex networks of relationships instantly. So today we're doing a deep dive into property graphs and the Cypher Query Language, which totally rethink how we store, query, and evolve data to match this modern reality.
To really set the stage here, I want you to imagine a fundamental question. How do you model a world where absolutely everything is connected to everything else? In traditional relational databases, we're super used to neat, predictable tabular models, right? You have your rows, you have your columns, easy. But imagine trying to use those traditional tables to map out complex, sprawling, many-to-many relationships. You end up creating a join table just to connect two entities, and then, another join table to connect a third. Before you know it, you're trying to traverse 5 levels deep. Think about the technical cost of that for a second. Sure, the relational model can handle simple cases, but forcing heavily interconnected data into rows and columns, it isn't just unnatural, it actually leads to massive performance degradation. Your database suddenly has to scan and compute the intersections of multiple massive tables for just one single query. It quickly becomes an absolute nightmare of complexity and processing overhead.
And honestly, you see this breaking point all the time in certain types of apps. Think about highly connected data environments. We're talking about social graphs, where the vertices are people and the edges indicate who knows whom, or the web graph, where pages are linking to other pages, or even road and rail networks. The junctions are points on a map, and the paths between them represent physical roads. In standard transactional data, like say a traditional bank ledger, the entity itself is the star of the show. The deposit or the withdrawal stands alone. But in these highly connected environments, the relationship is just as important, if not more important, than the entity itself. And that right there exposes the fatal flaw in the relational model. When your data naturally looks like a social network or a city roadmap, the relational model just completely strains under the weight of endless joins. The more hubs you need to make to find your answer, the exponentially slower and more complex your SQL queries become.
Okay, let's jump right into our deep dive, the anatomy of property graphs.
At its absolute core, a graph simplifies the world down to just 2 fundamental building blocks. It's a data structure consisting of 2 kinds of objects. First, you have vertices. Depending on who you're talking to, you might hear these called nodes or entities. Second, you have edges, which are the relationships or arcs between those entities. Whether you call them nodes and relationships or vertices and edges, the underlying philosophy is exactly the same. You are elevating the connection to a first-class citizen in your database. Rather than building dozens of tables with varying schemas to artificially fake these connections, you're modeling your entire domain using exactly what exists in the real world, things and the connections between those things.
To really anchor this concept, let's look at a slice of life for 2 people, Lucy and Alain. As you can see, Lucy is from Idaho and Alain is from St. Louis in France. They're both represented as distinct person vertices. But look right between them. There's a direct edge labeled married. From here, we can intuitively trace their geographical and social paths. Just follow the paths with me. Both Lucy and Alain have a lives-in edge pointing to a vertex for London. London then has a within edge pointing to England. England is within the United Kingdom, which is within Europe. Now let's track backward to where they were born. Alain has a born-in edge pointing to St. Louis. St. Louis has a within edge pointing to Normandy, traversing up through France all the way to Europe. Lucy's born-in edge points to Idaho, navigating up through the United States to North America. By just walking these paths, you effortlessly understand the deep, multi-layered history and current reality of these 2 people, all without writing a single complex SQL join. How cool is that?
So, in the property graph model, we distinctly separate the things in your data from the connections between them. A vertex has a unique identifier, a string label describing what type of object it is, like person or location, and crucially, a collection of key value properties. And that right there is exactly what makes it a property graph. Vertices aren't just empty dots on a whiteboard, they hold rich data. For example, the Lucy vertex has a property for her name. A location vertex for London might hold properties for its total population or the year it was founded. The edges sit completely separate, but they're intimately linked to these vertices, managing the incoming and outgoing flow of all these varied relationships.
Now, if we zoom in on the anatomy of an edge, we see it actually brings its own rich context to the party. Every single edge has a unique identifier and, importantly, a specific directional flow. It has a tail vertex, which is where the relationship starts, and a head vertex, where it ends. You might be wondering, why does direction matter so much? Well, because relationships in the real world have direction. Elaine was born in St. Lo. The relationship points from Elaine to the city. Obviously, the city of St. Lo wasn't born in Elaine. The edge also has a label describing the kind of relationship, like married, lives in, or within. And just like the vertices, edges can have their own properties. You could totally have a married edge that contains a key value property for the exact date the marriage took place, or a road segment edge that tells you the physical distance between two junctions.
But here's the real kicker: supreme flexibility. In a property graph, any vertex can have an edge connecting it with literally any other vertex. There is no rigid upfront schema dictating what kinds of things can or cannot be associated. Contrast this evolvability directly with SQL for a second. If tomorrow you wanted to add food allergies to our graph of Lucy and Elaine, what would that require in a relational database? Well, you'd need to design a new schema, write migration scripts, schedule some downtime, and refactor massive tables just to fit the new foreign keys in. In a property graph, you wouldn't need to fundamentally alter anything at all. You just introduce a new vertex for the allergen, say peanuts, and literally draw a new edge from the person to the allergen. Done. You can continuously add new relationships and completely new types of data on the fly, all while keeping your model clean and highly adaptable.
All right, moving on to our next deep dive section, querying with Cypher.
So, now that we know how this data is stored and structured, we need to talk about how we actually get it back out. That brings us to Cypher, which is a query language specifically designed for property graphs. Originally built for the Neo4j graph database, it's since become widely adopted across the industry. Now, Cypher is a declarative language. Why is that so powerful for graph data? Well, in an imperative language, the developer has to worry about finding the optimal path. You have to tell the computer exactly which operations to perform and in what order to find the data. But with a declarative language, like Cypher, you just describe the pattern of the data you want to find. You describe the conditions the results have to meet, and the database's query optimizer takes that cognitive load entirely off your plate. It figures out the most mathematically efficient way to navigate the graph to find your answers. I absolutely love this next part. Notice Cypher's visual arrow notation? It basically looks like ASCII art. Look closely at the syntax here. You use parentheses to represent the vertices, so the tail on the left and the head on the right, and then you use dashes, an arrow, and square brackets to represent the edge and its label connecting them. It literally looks exactly like the graph paths it's searching for. It reads from left to right exactly how you would trace the logic out on a whiteboard. Parentheses, dash, bracket, label, bracket, dash, greater than sign, parentheses. This is such a brilliant design choice because it means the code you write mirrors the human mental model of the interconnected data you're querying. Okay, let's put this to the test with a real-world scenario. Let's look back at our graph containing Lucy and Elaine and perform a pretty complex task. Think of this as a massive logic puzzle the database has to solve on the fly. The question is, find all the people who emigrated from the United States to Europe. If you break this down, the database needs to find a person, look at where they were born, traverse upwards through a geographical hierarchy to see if that specific birthplace is ultimately inside the US, and then look at where they currently live and traverse upwards through that separate geography to see if it ultimately lands in Europe.
The absolute hardest part of this query, and honestly the thing that makes it nearly impossible to efficiently hard code in a traditional database, is that geographical hierarchies vary wildly. A person might live in a city, which is within a county, which is within a state, which is within a country, or, they might just live in a standalone territory. You simply do not know how many unknown layers, or hops, it takes to get from the person's location vertex to the target United States or Europe vertex. The database doesn't know the depth of the graph until it starts walking it. In the biz, this is called a variable length traversal. Cypher handles this unknown depth elegantly with a 0 or more operator written as *0 ... inside the arrow notation. It essentially tells the database engine, hey, follow the within edge 0 or more times, however far it takes until you find what I'm looking for.
So how long does it take to write that kind of query? That incredibly complex query, navigating multiple unknown layers of geography, intersecting personal history, and scanning variable lengths, takes exactly 4 lines of code in Cypher. Just 4. Listen to the simplicity of this logic. Match the person, follow the born-in arrows 0 or more times to the US, follow the lives-in arrows 0 or more times to Europe, and return the person's name. It is highly readable, remarkably concise, and entirely focused on the pattern rather than the clunky mechanics of the search. Now brace yourself. What happens if we try to do this exact same operation with relational tables? I mean, you can technically represent graph data in SQL using edge and vertex tables, but to handle that variable length traversal, where you don't know how many joins you need in advance, you have to resort to recursive common table expressions, specifically the with recursive syntax. Lean in how painful that is for a moment. Attempting that exact same variable length traversal in SQL requires 31 lines of highly complex code. 31. It requires the developer to build temporary virtual tables in memory, define base cases, join them iteratively until all possible edges are visited, manage infinite loops, and then finally intersect the results. It is an immense amount of cognitive overhead and a massive headache for the developer just to ask a relatively simple real-world question.
And this right here? This brilliantly illustrates the aha moment of graph databases. On the left, Cypher gives you 4 elegant lines of visual pattern matching. On the right, SQL gives you 31 clumsy, exhausting lines of recursive statements. It's not just about writing fewer lines of code, though. It's about semantic alignment. Cypher maps directly to how humans actually think about relationships. SQL, in this context anyway, forces humans to think like relational machines. It just shows how much of a difference the right choice of data model and query language really makes. When you match the correct query language to the proper data model, you exponentially reduce the complexity of your application's logic.
All right, let's bring it all together. Summary time. Key takeaways.
Let's synthesize what we've learned today. When your application relies on heavily connected data, where many-to-many relationships are the norm rather than the exception, the graph data model provides absolute superpowers. Property graphs break the complex world down into simple, flexible vertices and edges, totally untethering your development team from rigid schemas. Cypher leverages declarative visual arrow notation to make querying highly readable and mathematically optimized. And importantly, by leaning into variable-length traversals, graph databases drastically outperform recursive SQL, turning 31 lines of painful logic into just 4 lines of elegant pattern matching. All of these components work together beautifully to elevate the connection itself to the center of your architecture.
I want to leave you with a final thought to ponder. As you step back and consider your own projects, or maybe your next major feature launch, ask yourself this: is your current database schema actually choking the evolvability of your application? Are you forcing wildly interconnected data into traditional relational tables? And is that the very thing holding your development back? Understanding property graphs gives you permission to stop fighting your data and start letting its natural connections drive your insights. Thank you so much for joining me on this explainer. Keep questioning your data models, and I'll see you next time.